Everyone, thank you guys for being here. I'm sorry for the 5 minutes delay. I'm not particularly sure what happened, but my computer was acting up. So let's jump right into it since I'm already behind schedule. I'm going to share my screen right now. How's everyone doing? Did you guys have a good day? Oh, thank you, Charles. Shout out to you. Shout out to you.
Yeah,
Me too.
we had a good day.
Yay, that's good. I'm battling screen problems or computer problems. But that's okay because we will come out on top. Okay, wonderful. I'm going to have to turn that off briefly so I can move it to the.
Yeah, it's visible.
Okay, fantastic. So hi everybody. Like I said earlier, my name is Princess, and this is going to be a session that covers system thinking. The general idea is that because the main job of manual syntaxing has been, completely given to artificial intelligence, we need to improve our thinking as engineers, because usually you would get applauded because you wrote a very good function. However, that is no longer enough. So first things first, I'm not even sure. I don't know what's happening today. Oh, shoot. Okay. Okay, so this is going to be a preview. I'm going to introduce myself. I'm going to talk about why this, a quick quiz, the AI impact gap, the engineer's true goals, the tinkering framework. We're going to discuss two paths, and that this will make sense later on. A fintech scenario, and then we're just going to close. I know it seems a bit short, but I think it will make more sense when we, get deeper into it. So a bit about me. Like I said earlier, my name is Princess. I did my undergraduate in computer engineering at Covenant University in Nigeria. I'm currently doing my master's in applied computer science. I have 2 certifications from GCP, one of which is a professional networking certification. I was top 5 in a Google hackathon that happened last month. I was the previously product designer at the microfinance bank in Nigeria and a fintech that operated in Canada. And currently in Vera, it's a solution to the AI hiring crisis currently happening. But that's not why we're here. So why, you guys are still following me, right? You need to talk to me, okay? So everyone can hear me, can see my screen. Are we good so far?
Yes, we can hear you and we can see your screen.
Okay, thank you. So why this topic? The shift in technology has become very apparent. I think right now, if you're peddling yourself as, let's say, a DevOps or a cloud engineer or an infrastructure engineer, even a software engineer, you're going to quickly see that nobody really cares how much code you can write anymore. So that has really taken away from people whose major, I guess, selling point was that I can write code. The era of coding as a skill has come to an end. And then thinking clearly has never been more important. So this is exactly what this session is supposed to teach. It's supposed to teach each and every one of us how to be better engineers, how to handle problems, and just how to move from, I guess, a reductionist mindset into a much more holistic view of the system. So let's see. Let's move to the next slide. I don't even know what's happening today. I guess it's just not my day. Okay, so I did this quick quiz for everyone. If you can just quickly bring out your phones, and just answer, I guess. The quiz is just to get everybody thinking generally, what exactly is the cloud? Yeah. So I'm just going to wait for some people to answer the question. Just bring out your phone, scan the QR code. Yeah. And your answers will be displayed, obviously. So now I'm going to, this is where all your answers are going to show. Obviously, your names won't be part of it. I'm wanting 6 participants. Come on, guys. This is supposed to be interactive, okay? No answers, no trials, no attempts. Okay. 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 Rented computers. Okay. Okay. More answers, please. I'm curious. Let's. Okay. Just try not to. Okay. Well, anyways, a machine as a server, an online machine. Okay. 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 I'm going to leave it on for maybe 20 more seconds. Well, that's okay. I'm very thankful to you guys who participated. I love a good participation. So beyond a system, beyond let me use the answers you guys used. Beyond rented computers, an online machine, and I know that most of your answers were cut short, a server and things that you don't host. Beyond that, a cloud is an interconnected system of technology, right? So beyond the server, you can have databases in the cloud. You can normalize data in the cloud. Heck, you can even implement an infrastructure that reduces code loads, because most of the work is in the infrastructure. Right, but we'll get to that in due time. So the AI impact gap. AI has made syntax generation fast and easy, and this has caused a massive explosion in raw code volume. However, without humans governing this architecture, this automation introduces severe challenges, risks, and compounding technical debt. So if you look at the stats I've put in front of everybody, 70 to 90% of Anthropic's production code is written by AI right now. There has been an 8 times increase in duplicated code blocks across software repos. A lot of companies, 88% tech debt spike is insane, because we were already battling tech debt previously, and now it's gotten much, much worse. And 45% of AI generated code fail standard security tests, and they introduce more vulnerabilities. So what does this tell us? This tells us that in as much as the syntax has been given to artificial intelligence, agents and whatnot, a good infrastructure, a secure infrastructure, an infrastructure that is resistant, is something that still deeply relies on the human. And even if artificial intelligence might assist you, which it definitely should, in let's say generating an entire Terraform document, because it can do that, the burden of the work still falls on you. You need to know why. Sorry.
Ah,
Hello. Hi. Do you want to ask a question?
okay. Yeah.
I think you can mute her. Elizabeth is not beside the computer.
Yeah, I don't think I have the power to mute. I think that was
Uh,
me.
Mute me,
alright.
please. I'm using my phone. Please mute me. I don't know that. Oh my God. So sorry, please.
It's
I don't know.
okay. It's
So
okay.
sorry.
It's okay. It's okay, darling. That's no problem.
Yes.
Oh, thank you very much, Tara. Much appreciated. So where were we? We were getting acquainted with the AI gap, right? So now that we've seen that artificial intelligence is some tasks faster, the job of thinking and tinkering has fallen solely on the human being. Would you be able to, because nobody is going to blame AI. If I think there was a I've forgotten the case study, but last year, 2005, yeah, 2025, September, there was a big problem regarding a 40 kilobytes file that was uploaded that was merged into production, and it caused a massive outage in healthcare. Nobody's going to blame AI for generating that. It was left to the person to understand that this doesn't belong in my system. This doesn't belong in our system. So yeah, that's that. So what are the true goals of an engineer? Because at the end of the day, whether you land a job, and I pray, we all land jobs, whether you are starting your own startup, whether you are coding for fun, whether you are building for fun, at the core of it, you are an engineer. The roles have multiplied vastly. DevOps, DevSecOps, I think, infrastructure, platform, cloud, and the names go on. But at the end of the title, everything still carries the engineer title because that's what you are. That's what we all are. So the goals of an engineer includes, but not limited to, translating chaos, managing failure, and optimizing constraints. So we're going to start with translating chaos. This is very interesting. So for anyone who has ever worked at a company or had their own startup, you understand the concept of translating a problem statement into something that is workable. I'll give an example. So I was recently having a conversation with one of my friends. He's a product manager he's a product / stakeholder manager at some company. It's an investment company. And the question of using AI to detect anomalies came up. How can we detect when a user's behavior has changed without flagging it wrongly, which is a very common problem right now in the fintech space, in the financial space generally. It was just a word that he uttered. And from that word, I was able to translate it into an infrastructure, translate it into some sort of visual block, explaining that if we're going to do this, not every block would need to collect data, because if you're going to collect data, you're going to have to normalize the data, right? And you cannot put that amount of stress on one system to collect, normalize, and still perform the task. And that is where separations of concerns come in. Okay, so I'm not going to get deep into that conversation, but the general idea was that a word problem was thrown at me. And because of the ability to think in systems, I already started saying something. Because as an engineer, I don't believe that a question or a word problem should be thrown at us and then then we cannot provide some sort of solution. Your solution might not be correct off the bat. I don't even think that's possible, but you should have a starting point. Like your brain should be able to piece things together. And that is the core of systems thinking, that you're able to piece things together, know where certain things live, but we will talk about that later. So the second is manage failure. This is really, can other people hear me? Someone can't hear me.
Yes.
You can hear me?
Yep.
Okay. I'd like maybe one other person to confirm. Okay. Okay. Thank you. Thank you. To the person who couldn't hear me, would you like us to wait for you? So while you fix up. Is he still on the call? Oh, well, I got no response then, so let's proceed. Okay, so managing failure. A lot of engineers, I mean, obviously now, well, no, a lot of junior engineers don't design with failure in mind. So it's like most people design and then they don't put into consideration that, oh, there could be latency. Oh, the API might need time to reset itself. You know, these little bottlenecks that inevitably happen because they have to happen. It's a system that processes data faster than it has ever processed before. So of course there would be failures. A good engineer, one of the true goals of an engineer is how to manage it. If something fails, your entire system shouldn't crash. Either the blast radius is minimal, or there is some sort of graceful, exit. Optimizing constraints. So this is very advanced engineering. I don't expect one person to be able to do all these three in a large or in a company generally, but you should, as an individual, have an idea of each so that you're able to ask questions. If anyone approaches any of you and they go, oh, I'd like you to be the CTO, you aren't just, thinking about just the first two or the first. You're actually thinking about how can I optimize constraints. So constraints might include the cost, the reliability, the performance, and just the structure of the entire infrastructure. That's cool. Under stress, because your system needs to be resilient. So these are the true goals of an engineer. It might be oversimplified, but I do believe that if you master these three, you can kind of fill in the gaps in case there might be small things in between. Okay. I keep doing this. Okay, so what is systems thinking? This is where we introduce it. So from here, we're moving from isolated components to interconnected ecosystems. Just going to read from the slide here. Systems thinking is the engineering discipline of seeing the whole picture. It focuses on relationships, linkages, and feedback loop between components rather than just analyzing the individual parts in isolation. So what does that mean, right? So, like if you think about it, a system isn't. My mouse is a system, right? It has multiple components that interact with each other for me to be able to use it properly. If, let's say, the sensor that guides the arrow is faulty, then it messes up the entire system. So you see why it's very important that you don't just see things in isolation, you see them as a whole. You're able to see the picture, and even if you might not necessarily. So let's say, for example, now like a big company, an enterprise company, let's say Meta, right? You're putting, you fall in the ads. Yes, you're in the ads, that's advertisement section of the company. When you think advertisements, you should already be thinking about data, lots of data engineering like you've never known before, and some other things, right? So systems thinking might not necessarily be you knowing how the entire meta works. No. But the ads alone is a working, living, breathing system that supports the rest of meta. I don't know if I'm making sense. But the idea is not to just see it as I am doing my part, right? How you become a good engineer, because at the end of the day, we all have to be good engineers. By the time you land the interview, you land the job, what keeps you is your value. And if you're not able to offer value, it just becomes like, what was the point of even struggling to get the interview, to get the job at the end of the day? Okay. So I came up with a framework because what I want us to do is approach systems as kind of a puzzle. How does it fit? Where does it make sense? So I came up with 4, bits and bobs systems: the power, the workers, the medium, the fail-safe. So I'm going to walk through them one by one. So for the power, that's, the engine. What drives the system? What is the source of the energy, data, motivation? Basically, what powers this thing? Why should I care about it? For the cloud now, we're looking at things like the CPU. I mean, AI, we are looking at the GPUs, because you need to put these things into consideration. Whilst building this tool I'm building, I realized that I was hitting a token button. Teach myself token optimization, or well, I guess they call it token engineering, to engineer my product to be able to use tokens properly. That's a power thing. It's no longer an application thing. This power is affecting how my application performs, the system. If the system stalls, I put an example of a question you can ask yourself. If the system stalls, where is the bottleneck? Is it in the energy or is it in the data flow? So energy is things like, the CPU. This is if you are, no, I'm so sorry. I'm being distracted by the auto plans. I'll just move on. But very quickly, this is the part where you ask yourself, I think CPUs are mostly already solved, but like take, for example, let's say you want to quickly train a model by your own self. You wouldn't do that on your computer because it would melt your computer. Melt is an exaggeration, but you understand. And that is a power constraint. So things like that, really. The workers, these are the executors, the execution. So this, what actually does the job? The executors, really. So now this is where you start asking yourself, is this specific tool the right fit for, this load? So take, for example, I'm thinking about something off the top of my head. So let's say you design a website that serves images to people in different geolocations, right? And someone from, let's say your main server is hosted in Europe West 2, right? But you have a user in Japan that wants to use that. Let's not even get into the insane latency that is going to give. You now need to ask yourself, if I want to reduce the time it takes for my user to get this content, what kind of tools would I use? So now you have a question. This is a question that you can take to AI It's a question that you can take to textbooks if you're still a bit old school. There's a question that you can take to like a senior infrastructure engineer, because knowing how to ask questions, the right questions, is a very, very important job. But you can't know how to ask the right questions if you are still looking at things from an isolated point of view. By the way, the answer to that would be something along the lines of like you create like a CDN, so that is cached at edge locations, so that way you can just serve it directly. But the fact that you understand this is the problem and this is the solution, or this is the problem, how can I solve this problem? That already puts you, I guess, 70% away from actually solving the problem. The medium, the connector. So what connects everything? The networks, the communication. Oh yeah, the workers, by the way, an example of that would be your virtual machines. There would be your, containers and the likes, your serverless functions, all those things. These are your workers. These are your executioners, I guess. So now we're going to look at medium. What connects everything? The networks, the communication protocols, the databases. So this is basically how things talk to each other. So at this point, you can ask yourself things like, where is the data dropping? Is there corruption somewhere? At this point, you are following the data, or you are following the traffic. So you know exactly where bottlenecks are, and you can you can quickly fix it. Fail safe. So this is what stops the failure from spreading. Most people would attribute fail safe thinking to a much more advanced engineering personnel, but I think anyone who is curious enough to learn would definitely want to understand the full picture. That's for sure. Right. So here we're going to look at two paths. Path A happens when you have inherited complexity, which is going to be most people's reality. At this point, you have joined a company or you've joined a group. This system was not built by you. We just saw earlier that 88%, I think, of companies are now in tech debt. There's nothing you can do about this, because at the end of it, this is going to be the reality of most people. You're going to face a system that was already built by someone. Most likely it was built in a hurry. A lot of things were not taken into consideration. So how do you approach that kind of system? Now, this is where you start asking yourself questions. Okay, what is the major power source of this? What kind of systems are we using? So for GCP, GCP hosts ourselves. Is this system, does it use a virtual machine? Does it use containers? Are we using Kubernetes? Are things already in, Terraform or infrastructure as a code? Like, these are the questions you can ask. Now, if the answer to these questions are yes, we can now ask ourselves, so what talks to what? Where needs to talk to what? So like, as you are formulating these questions, you're getting a bigger picture. You're asking the right questions. You're also proving to the person who you are working with or working for that you are interested in understanding this system as a whole. Yes, there may be documentation available. Most people try to put their documentation into like an LLM to read it and explain it to them. Please don't do that. Sometimes companies put some sensitive information. But generally, if you read the documentations properly, you would get a high level understanding of what's happening. And you can write it, ask your questions, because you're only as good or you're only as well equipped as the information that you have, right? So I give an analogy of a traffic, I'm sure you can see the cute little road there. A congested intersection isn't solved by widening it, hardly ever. You look upstream. So you start looking at things like, at what time does this happen? Does this happen by 3 p.m. every day? If this congestion happens by that time every day, then you know that it is a problem that is beyond the size of the road. You know, you look at things like, is the traffic light okay? There are other things that you look at, because nothing ever happens in isolation. While, yes, we separate concerns so that, you know, I mean, it makes debugging much easier, and then we know where the code lives. So if we need to upgrade the code, we know where to go to. Separations of concerns now also means that most systems depend on each other. So there's a dependency that forms. They kind of lean on the other, you know, I guess code or function or whatnot, or infrastructure. They talk to each other. So a database running at 100 capacity is hardly ever solved by scaling up. So this is where a lot of people do these things, and then you see your AWS bill running up. I'm not in GCP currently. My FinOps, so FinOps is your financial operations. Basically, it's your ability to manage finances and costs within the system. My score is currently higher than the average GCP engineer by a lot. I think the current average is 2.1/5. Mine is 3.3. I'm still building it up, definitely. And the reason for that is because most people think the issue is always to scale up, let's make it bigger. But no, the scale up is sometimes good, but for the most part, it's not. This is where you now look at it. You can even map it out if you need. I think I have an example of a system that I quickly mapped out, because I want to show you guys, as a cloud engineer, your mapping out might not necessarily mean, oh gosh, I cannot find it, guys. Now, I want to show you guys. Okay. I cannot find what I am looking for, unfortunately. But the general idea that I was trying to show, and I guess I could even just like give a quick example now, is that like as a cloud engineer, as anyone who works in the cloud who sees a system, because that's what the cloud is a system. You can do literally anything on the cloud. And when I mean anything, obviously within reason, please always consider ethics. That's extremely important, always. But if you have like a paper and a pen or an iPad like I do, you simply start sketching. This would probably be more interactive, but you simply start sketching. You can tell yourself that this is where I want this system to be. You can name it System A. It talks to this system via this, and you can start labeling it. From this short little diagram that we've seen, as a system engineer, as any form of cloud-related engineer, you can start building on top of that. You can see that, okay, so if I need this particular block in this system to process data, to clean data, and then to store the data elsewhere, I can just start asking myself, what kind of medium, what kind of workers do I put in that block to achieve the goal? So yes, a database, and again, like I put the answer there, the answer is rarely ever scaling up. Sometimes you try, it's called an exponential back-off retry. That's what it's called. Generally, what that means is that it retries, it weights exponentially by the last time it's retried, and then when it gets to a particular threshold, it stops replying. I actually just implemented that in my product. So what does that mean? let's say your API, right? Like you designed an API, you're a platform engineer, you've designed an API, for lack of a better term, that the rest of the development team you're supposed to ingest, right? So if, let's say, 40 engineers at once are trying to query the API, it might get tired, or the database, it might get tired. So, or it might just get tired, it might start throwing a fit. So what you can do is that instead of the thing to crash, the database itself or the API should be able to tell itself that if I fail the first time, I'm going to wait 1 second and retry. If I fail that second time, I'm going to wait 2 seconds. So that's where the exponential comes from, and retry. If I fail the second time, I'm going to wait 4 seconds. So now we've gone from 1 to 2, from 2 to 4. We're going to wait 4 seconds and we're going to retry. So some people some people like their own to get to as high as 24 seconds. I usually cap mine at 16. Because then if it has retried that much times, it means that there's something wrong. Then we can investigate further. There's this concept in philosophy. It's called the Occam's razor. I've forgotten. I think so. But the general idea is that if the answer to an assumption has too many links, then the assumption is wrong. So what does that mean? Let's say someone broke into your house now, right? These are two responses. The first response is, okay, an armed robber broke into the house. That's one response. The second response is someone lost their way, and the "and" now has given us another link, and they saw my house, and so now we've gone from the first simple answer to an answer that's now interlinking 3 different answers together. So at that point, we know that our first assumption is what we're more likely to go with. That is the same approach to take to the cloud generally. You start with your first assumption, looking at the logs. Then if you identify this bottleneck and you see that, okay, it's not fixing it, we can now add another "and." Okay, and so that's how you investigate. 9 out of 10 times, before you get to the third "and," you've most likely solved your problem. And if you haven't, there's a high chance that the infrastructure might be a bit wobbly. Round up 15 more minutes. Okay. So the clean slate. This is hardly ever most people's paths, except of course you're building your own thing. But at this point, this is a brand new system. It's so easy to just want to dive in and like, okay, yeah, I'm going to deploy a virtual machine. I'm going to do this. I'm going to do that. But no, I need everybody who's on this. You need to take a step back, right? Like you need to really step back. If you're going to start with the PRD, or you're going to start like writing out a documentation, because you need to know what you want to do. Then once you've converted that into a word problem, you now need to ask yourself, how can I model this world into a system that the computer can take? So how can I transform, we need an app that can scan flowers or scan plants and give us what is wrong with the plants and treatments for the plant. How can I turn that statement into an engineering problem? So people just like to like the era of diving into code is dead. And to be fair, even when like code writing wasn't so wasn't automated, even when code writing was automated, the major difference back then between senior engineers and junior engineers were senior engineers understood this. They understood that you don't just run into the code, hardly ever. And by code, I mean, I know that we're thinking, oh, we're cloud engineers. I mean, Terraform count as a code. Yeah, infrastructure as a code. Scripting, I mean, these things. So yeah, You don't do that. You ask yourself, how do I translate this into an actual problem that is solvable? Because the moment you are able to model the system, you've already solved most of your problems. That's just the truth. I mean, obviously, we now have to start doing things like dependencies, but containers handle that for us, and Kubernetes handle containers for us. So you see how with the modern world of technology, the most important or valuable engineers are not the ones who are very hard coded on code or hard coded on, okay, I want to deploy a virtual machine, but they are the ones who understand the system and understand that various systems require different tools. Take, for example, I built a bot, right? So the bot I built, I wouldn't host a bot on Cloud Run. I wouldn't host it on any cloud network, on any cloud resource that is focused on containers. I also wouldn't make that a serverless function. It's a bot. So what do? I deploy a virtual machine. Because the world of today, I mean, everything has to be in a container, to be honest. I want to host a container. There's no need to spin up a virtual machine. I can put it in, specific resources that is designed for containers. So the challenge is not, okay, this is what I need to do. No. That's actually wrong. The challenge is not about the code or the syntax or understanding or cramming Terraform or cramming how to write a Docker file. AI can do that for you, clean, easy, in seconds. The challenge is, what do I want to build? What kind of system do I want this system to be? What kind of system do I want this to be? Who am I protecting? How am I protecting? When you ask these questions at the beginning and you actually map it out, you draw diagrams, you visualize the movement of the data, you quickly understand that what I want to do is not as hard as I thought. It just needed some organization. So yeah, clean slate is really important. It's also quite important because you don't want to now create the technical debt that some other engineer would be mad at you for. And also it's easier to, improve a system if the infrastructure is clean. I need to quickly rush through because I'm sure some of you might have questions. So optimizes individual isolated parts. You optimize the whole interconnected system. Right, relationships, how they talk to each other. You use AI to generate raw volume. So at this point, this is where people just do things like generate an app for me that does this. And I guess that's fine for like the average, user or the average LLM user. But that's not you. You are supposed to be an exquisite engineer, somebody worth their weight in gold. Or this AI to prevent technical debt, debugging, fixes immediately localized symptoms. So that's when people try to use code to fix a problem that an infrastructural improvements can change. So a systems thinking engineer traces the engineer might assume that components will not fail. But as a systems thinking engineer, you should be able to contain blast radius and just ensure your system fails gracefully. So the future belongs to engineers who can orchestrate the chaos. AI has permanently solved the bottleneck of writing code. That's just the truth. The Docker file, the IAC file, even the CI/CD pipeline, that is going to generate the code for you. That's easy. However, you are the only one who can really architect the problem, artificial intelligence, to create a much more interesting infrastructure. When I say interesting, I mean resilient, scalable, and all that good stuff. Yes. Has permanently solved the bottleneck of writing code. Your value is no longer measured by the lines of syntax you produce, but by the resilience, security, and scalability of the architecture you oversee. So that is it. I hope you guys learned something, and I am open to Q&A. Please ask me questions. I have been talking, and I want someone to talk to me. No questions? Everything I presented was that clear. Well, kudos to me then. Okay, well, in that case, I guess I can stop sharing my screen. So thank you all for participating in this. I'm really thankful to Tara. I'm thankful to the entire team at the university. This was a really, really amazing opportunity for me.
Thank you so much.
Sharing this, and I do hope that at the end of this, everyone has kind of walked away understanding what's being with little tools to answer questions. You know, like, oh, what are the mediums? Who are the workers? How are we connecting them? You know, what amount of processing power we consuming? The kind of questions that is expected of an engineer, you know, going forward. Thank you.
Thank you so much for and forward for the.
Okay, guys. 6 minutes clock. I mean, ask. We still have 6 minutes together. It doesn't necessarily have to be about system. It could be about.
I think people will.
I don't know how to do that, dude.
I will share something with you on WhatsApp or on LinkedIn.
Okay, no problem. I'll be looking forward to that. I'll put it up. No problem. Okay. I think like the third time I'm going to say thank you, but this was an amazing opportunity for me. Yeah, just go out there, be confident, read more, because as an engineer, reading is very important. And ensure that any job you bag, any job you land, when they call your names, they say to themselves, that is a very good engineer. That's very important. I guess I'm going to have to drop off now. Bye, guys. Thank you so much for coming.
Thank you too.
Bye.